Welcome to week one of ReproRehab. I'm David Kennedy. Today, myself and JB Pauline will give you some of the overall principles of reproducible sciences. We'll get JB's perspective on that. Then I'll return to you and give you, my perspective, and then we'll dive into some of the statistical implications that are important for us to be considering back with JB. So without further ado, I'll turn the floor over to JB.
Hi everyone. This is an introduction about the reproducibility in the life sciences, and I will base that introduction with some examples. My name is Jean-Baptiste Pauline, and I'm working at the Montreal Neurological Institute at the Brain Imaging Center. So first of all, why did people started to really think about the reproducibility aspect in life sciences, and why is it important? I just want to give you this quick view of the problem. It seems that we have an increasingly large body of citations and large body of papers. For instance, we're using this recent work in PNAS, the 1.8 billion citations, 90 million papers across many fields of science. But it doesn't look like progress is made very rapidly because of this increase of body of literature, and sometimes it actually feels like the increase in the number of papers is actually making things worse in some ways. And so therefore there's a lot of reflection on how do we improve globally the research, and and maybe comparing like what life science does compared to what the to physics does, for instance, in the when a result is actually very solid, and in physics it's well known that this is like a 5 sigma sort of threshold, which is definitely not the one we're using in life sciences. So the cause of this ossification of progress are complex and numerous. I'm not going to really dive into those in this short introduction. I'm just going to give you some example of why people started to worry about irreproducibility. Before I do this and take examples, I will just remind everyone that reproducibility is a kind of an ill-defined term. And so I'll take this grid of which is, I think, the most used terminology, where reproducibility is about really being able to launch the same data on the same data, the same pipeline, the same analysis. While if you're thinking of having a different data set, we're talking more about replicability. And if you're thinking about using the same data set, but a different type of methods, similar pipelines or similar algorithms to get the results, then this is more on the side of robustness. However, I think the right way of thinking of reproducibility is really generalizability. In what dimension is your result, our results generalizable? Can we take another similar data set, and are we likely to get the same results? Can we take a similar pipeline? Are we likely to take the same result? Can we do it in another country? Can we do it in another in 1 year time? Or like all those things are generalizability aspect with respect to some axis: data, pipeline, time, stimuli, and so on. So that's really the right way of thinking of this problem. But reproducibility has been taken as the generic word for all those things, and so I will use that word and that term in my introduction. So one of the, I would say, one of the first wake-up call that came in that field of research is the little study. I mean, not little, like the study by Amgen in preclinical cancer research. And the Amgen is a small pharma that was interested in looking at the very groundbreaking and very highly cited and very in high and published results in a high journal in a high profile journals, and they took 53 of those very high profile papers. And then they tried to look at how they could actually reproduce the results for their own, development of drugs and so on. And after a year or two, talking to the authors, talking to trying to replicate within their labs, or even actually going sometime to the author's lab and so on, they were actually only able to replicate 6 of the 653 results. So a very poor percentage, and maybe something like a 20% where intermediate results were replicated. So this was like a little bit of a shock to I guess NIH, with mostly funding this research, but also to the community at large. More recently, very interestingly, the reproducibility in cancer biology actually tried to replicate also some preclinical. Redid that kind of study, and while they found a bit better result, the still results are very are not really what we would like them to be. And there's a lot of impossibility of trying to do those things, because the number of details that are available in those papers are not enough to actually reproduce the results. Another key study, which I found very, very interesting, is the forensic analysis from Bagley and Combs in study, published in 2009, so quite a while back. And I think that's very interesting because you may have heard about the Potty scandal and the Duke scandal, but I think very, very little of the actual problems with reproducibility is coming from fraud in our fields. Most of it is from other factors. And this study is interesting because it didn't start, as the authors were not fabricating everything. The very first results were not fraudulous. They were just mistakes being done. And what happened, so this is a study about the cell lines, and the authors were looking at whether those cell lines were more or less resistant to drug or sensitive to drug, using the genetic profile, expression profile. And so they were building a model to that, trying to predict which patients will actually be good responders to specific drugs. So very interesting in principle. But the problem is that when those researchers were asked, whether they could help others to do the same kind of analysis in their home institution, they tried to reproduce the results, and they were unable to do this. But they were able to actually get to why the results were not reproducible and what was wrong in the analysis initially published by Potty et al. And they were able to do this because the data were available, the methods were available, and after a long time of struggling to know why they were not able to reproduce the results, they understood the reasons, and it seems that the key aspect was that some common lines were requiring two arguments, two Excel spreadsheet files as arguments. One of them was expected to have the headers of the columns at the Excel spreadsheet, and the second one was expected to not have the header of the columns, or the opposite. But there was a mismatch between that. So it was really a recipe for mistake, and indeed there was a mistake done at that level apparently, and therefore all the genes were shifted by one line in that Excel spreadsheet, that CSV file, whatever. And so at the end, Bagley and Combs really, thought about that the problem, and they said with poor documentation and irreproducibility, even well-meaning investigators may argue for drugs that are contradicted to some patients, because at the time where they were published, there was already, I think, some clinical trial being set up or on the way. And they thought about the problem very hard, and they concluded that most common errors in research are simple errors, like the row or column offset, and conversely, the most simple errors are quite common. And I think there was a very interesting so like wake up call of the community, with the little caveat that Bagley and Kuhn tried to actually publish these thoughts and their study in the original the original journals that were publishing the Petit et al. Studies, and they were not able to do so. They had to because they were Nature Medicine or and they had to resort to like a statistical journal, a biostatistical journal, to publish their results. More recently, but not very recently, the study by Nosek on reproducibility in psychology was very interesting as well. So the open science framework was actually designed and to actually make those studies more easy to do, and to as a response of the problem of irreversibility in psychology. So what these authors did was to take about 100 studies and give that to 100 labs or so, and those labs had to actually recruit new subjects, do the study, and then report the results. And what happens is that most of those studies were not replicated, but 40% seems to have been replicated, but with a much lesser effect size in general than the original published effect size. So that's an interesting aspect, which will be covered in the statistical part of reproducibility, and how do we deal with statistics in that framework. But that's what seems to happen. The effect size is clearly often overestimated in original studies. I want to take this other example because it's interesting for also for the sociological aspect of pipeline and software that are being shared or between the labs. So this is the story of this probably very good researchers. I mean, most likely very good researcher publishing in Science, PNAS, and all those high-profile journals. With on the crystallography, and he was using a specific program that was given to him by a lab that had done really good publications as well, and until someone realized that this program had a -1 somewhere in the code that shouldn't be there, and that was all the structure of the proteins were actually flipped, mirrored, and therefore he had to actually retract all those big journals, those big papers. And the sociology of it is that the trust was given, I think, because that pipeline was received by a lab that was actually doing some very good job, and that pipeline was also distributed to other laboratories. I think what's interesting here is that we tend to trust very kind of high-profile laboratories and that have done very good papers, and and often with good reason. That's a very reasonable thing to do, but that trust doesn't lead us to actually check things and to and do the series of check that we should probably do when we're using an external software. In neuroimaging, in more closely to my own research field, this is an example of a meta-analysis across almost 100 individual neuroimaging experiments, looking at the association between unipolar depression and brain regions, and this meta-analysis didn't actually show any significant result. while all the original studies, of course, had some insignificant results. So there was always this worry that individual studies are not often always to be trusted. They might be sound and reasonable, but they're not sufficient to actually establish something that we can rely on in terms of results. In the field of imaging genetics and imaging, I can think there was this interesting paper by Jason Stein a while back, showing that some actual hippocampal volume and some SNP, some association with a SNP with the hippocampal volume in a very large cohort. And the interesting aspect of that study is that none of the previously identified SNPs were actually found in this very large cohort. And there's a lot of in the field of imaging genetics and genetics, there's a lot of thought about the fact that the storytelling aspect of papers sometimes supersede the actual basic like a solidity of the statistics. So the conclusion of Jason is that biological plausibility is not a substitute for statistical significance or experimental validation. Yeah. One last thing which I thought was really interesting is there was an extremely interesting editorial that where the quote is that most of the scientific literature perhaps may simply be untrue, and in their quest for telling a compelling story, scientists too often sculpt data to fit their preferred theory of the world, or they retrofit hypotheses to fit their data, which is Hawking. And our love for significance pollutes the literature with many statistical fairy tale. We reject important confirmation. And so I was wondering who could have said that, and I was asking my students about that question. And was it Brian Nosek, like an open science advocate, and or our dean of the medicine at McGill, or the Lancet editor-in-chief? And he's actually the Lancet editor-in-chief, Richard Horton, who wrote that editorial. Which, if it can go at that level of consciousness, I think it is clear that we have a big problem in irreproducible science. So that all those things have led quite some response by funding agencies, the Wellcome Trust, NIH, and many others. And I think that paper for the plan for enhanced reproducibility by Collins and Tabak is one sign of that. I must say that that's 7-8 years later that Nature editorial. I don't think we have made fantastic progress in terms of irreproducible, incurring and mending the irreproducibility of our in-life sciences. So the problem is kind of widespread. It has touched also the consciousness of society at general. I just want to make sure that it is in the consciousness of every one of us, and try to understand what are the causes and what are the possible solutions and collective solutions that we can bring to that problem. Thank you.
Thanks, JB. That was a great introduction. I'm going to add some of my own sort of 2 cents to these sort of high-level principles of reproducible science, and we will, continue from there. Like I said, I'm Dave Kennedy. I'm at the University of Massachusetts Chan Medical School. I'm a professor in the departments of psychiatry and radiology there. By day, I work on child and adolescent neurodevelopment issues. By afternoon, I work on NITRIC, the Neuroimaging Informatics Tools and Resources Clearinghouse, and by evening, I help direct the ReproNIM program. As far as an overview for my presentation, I will echo some of the things JB has already talked about in terms of establishing that reproducibility is a problem. We'll review that in our very complex neuroimaging types of experiments, that so many of the details that we select matter and can affect the outcome, which really emphasizes the importance of transparency and describing everything that we do. We'll take that into the concept of a publication that is re-executable being the cornerstone of reproducibility, and that's something we've referred to as a ReproPub, re-executable publication. And then we'll look at sort of a framework for how we can take some best practices and apply them to the various different elements of our research program to try to increase the reproducibility of our overall efforts. In addition to all the types of things that JB mentioned, one of the quotes I come to very often was by Tom Insel and his colleagues back in 2012. Tom Insel at the time was the director of the National Institute of Mental Health, and he was lamenting that decades of brain imaging and genetics and all sorts of research has been going on, but that very little progress has been made in improving outcomes in mental health. And amongst the things that he points out is that there are a profusion of statistically significant but minimally differentiating biological findings. These all lead to a sort of approximate replications of these findings in ways that neither confirm nor refute them, and also that the focus on comparing prototypical patients to healthy controls, which generates limited clinical applicability. So this lament is partly to do with sort of the biology of the diseases that we sometimes chase in mental health being very spectrumy and may not be sort of therefore heterogeneous and therefore have challenging properties to distinguish what is autism versus schizophrenia versus depression and things like that, because they're very sort of heterogeneous types of differentiations. So this kind of concern led to the RDoC, the research domain of classification criteria that the NIMH has taken on to try to get away from diagnosis per se, but really getting to classes of symptoms and things that may span diagnosis as a more appropriate way to sort of characterize diseases and the issues that are related with them. But this also points to the fact that it's relatively easy to take a bunch of patients, do an imaging study, do some measurements, and look between groups and find something that shows up in your particular data set. What's been very hard is for these findings that individual studies make to, one, replicate across lots of studies so that they're and also to be while they're statistically significant, maybe what the biological significance of these findings are, is often quite questionable. So we end up finding things, publish things. We don't publish the negative things that we find, and we just build up more and more of these findings, all of which are limited in terms of the power and the studies that they're participating in. So again, we build up lots of observations, none of which that cohere into a synergistic view of what that disorder is doing. And JB already alluded to a lot of the issues that are behind this, sort of on the statistics and the sampling and other sides of things. So when we come to the idea of these approximate replications of findings in ways that neither confirms nor refutes them, there's some things that I think we can take home from that. The first concept is that it's impossible to confirm or refute something that you can't first replicate. Second is we tend to not publish findings with the necessary level of details in order to replicate our publications. And when it comes to examining re-execution and replication, everything that we do in our sort of research process matters. Again, the publication, the scientific process of taking terabytes of imaging data, running hundreds of hours of computational analysis and complex statistical interpretations thereof to yield a handful of conclusions is hugely reductionistic and hugely many variables that need to be characterized in how that process happened so that anyone else could have a chance in heck of getting through that process back to the exact same answer that you started with. So just a quick little summary of the various things that matter. The exact same software, the exact same software version can matter depending on what hardware it's being run on. The exact same question, the exact same software can care about how many data sets you have. You're looking at hippocampus volume as a sex estimate. If you have the 300 subjects of the NIH pediatric data set of back in 2005, you didn't really see anything significant there. Fast forward to 2011 when PING, the Pediatric Imaging, Neurogenetics, and Cognition study, came available. Then with a bigger data set, more higher quality data, then suddenly things become apparent. So again, the amount of data you have, the quality of the data, matters. What tool you use, matters. Again, there's many tools that do most of the different types of things we like to measure. And, while it's nice to, it would be fun, it'd be easy to say, oh, tool X that measures volume, is equivalent to tool Y that measures volume. Well, we see that's not exactly the case. Again, just a quick little example here of a particular anatomic region and two popular tools, FreeSurfer and ANTS, looking at the correlation of a particular measure between different versions of FreeSurfer. Fine, that looks pretty good. But then between different software packages, there's yes, a high correlation, but this is large, set of data. That correlation is not, super, direct. So there's a good bit of variance that's still introduced by different tools measuring comparable types of objects. So again, exactly what tool matters when you try to conclude something about a property of the brain. Exactly what statistics you use matter. This is just a little example of, the possibility of a particular, again, looking back at our sex in hippocampus statistical model, where we permute many different models that include age and sight and socioeconomic status and total brain volume and genetic ancestry. And with all those different model permutations, we can get lots of results, and the effect size depends on which model you're using, and the significance of those effects depends on what model you're using. Right now, we're not going to talk about what the right model is. We're just using this as an example to just document sort of how important knowing exactly what statistic you choose and you've reported is to the nature of the results that you observe. I'm going to highlight just super quickly something like what JB said as well. He looked at a study that started from a meta-analysis that showed something pretty clear, and then followed it up and said that even something that's in a meta-analysis, there lots of publications report something, doesn't necessarily mean that that's going to end up being the case. In this case, a paper by Anne Lefebvre and Roberto Toro that took this observation through many publications that the volume of the corpus callosum is reduced in autism. A meta-analysis shows a pretty clear effect that of the reported publications, there is about a 0.5 standardized effect size in the reduction in the corpus callosum in autism. Well, if you follow up that concept with a mega-analysis, analysis of the ABIDE, the autism brain imaging data exchange data set, and do a prospective, assessment, of the same particular observations, the corpus callosum as a function of diagnostic label, do we see the same type of thing? Well, when you do, that, we see significant side effects. Great, you expect that. You see significant age effects. Great, you expect that. You see significant sex effects. Yes, we expect that. But lo and behold, the group effect, the diagnosis effect, is not significant in this, sort of prospective mega analysis of a large data set. So the concern, of course, is that the size, an effect size of 0.5, Cohen's D, is really a pretty a relatively small effect, and all of the studies that went into that meta-analysis only had at most 100 subjects. So the power for in those studies to detect an effect of the order of magnitude of a Cohen's D of 0.5 was actually exceedingly low, and so when you actually do a properly powered study, and this study here has has 600 and some subjects, and is very well powered to see effect sizes of that size, and we don't see that effect. So again, the concern here is that false positives or limited observations and only publishing of positive results and not the negative results, can really yield a literature which is biased towards effects. And then when you do meta-analysis in that biased literature, you'll get a biased, meta-analysis. Now, in the end, it's not that nothing is going on between diagnosis and corpus callosum. It's just it's probably not a exact relationship between the volume of corpus callosum and the diagnosis. Indeed, IQ is related to these diagnoses. Indeed, brain volume is related to IQ. So it's a much more complex interplay between the brain volumes, the diagnosis, the IQ, and the corpus callosum volume. So something's going on, but again, unless we model it correctly and with the sort of appropriately powered observations and appropriately balanced statistical approaches, we're not going to see what we think we see and what the literature might have led you to believe. My version of one of the things that JB showed you, the spectrum of reproducibility. Again, we want to start from re-execution. If we can re-execute something, we can then have a proper framework upon which to study the generalizability of that finding. So re-execution of a particular publication with that exact same data and that exact same analysis should yield that exact same result. And if you can't do that to document that your data and your analysis have been transmitted accurately, then it's hard to argue that anything else beyond that is adding to the observations. So if you can get to re-execution that someone other than the original author can get to that exact same data, get to that exact same analysis, and document that they can get the exact same result, then you have a proper framework for exploring the generalization. Well, if we keep that same data but change the analysis method a little bit to still look at the observation of interest, but do it slightly differently, we can begin to understand how sensitive that finding is to the exact details of the analytic approach. Similarly, if I held that analysis constant, but brought in similar data, more data of the similar data type, or a different set of data of that similar data type, a true finding should also yield a similar result. So we want to get to this generalized finding, a true finding, really should not care exactly which 100 subjects with that disorder you use and exactly which tool you do, which valid tool you do that measures that measurement. If that's a true finding, it should be able to withstand those levels of generalization in order to really be confident in that finding not being a foible of your sample or a foible of your analysis. So philosophically, this cornerstone of reproducibility is transparency. Transparency is achieved in our publications through annotating and sharing with others precisely what operations were performed and exactly on what data in a fashion that could be potentially re-executed by someone in an attempt to replicate and ultimately document the generalizability of that original finding. So this question of how to write, therefore, a publication that includes all that information is a key thing that we need to worry about and sort of work on as a community to improve the way we publish our findings that approach that ideal. So this concept of a ReproPub, a re-executable publication, a ReproPub would include all of the words that we need. Humans need to read this and understand and comprehend what we're saying, but we need to supplement that one way or another with somehow a pointer to exactly that data with appropriate access controls that went into that particular analysis, a specification of the workflow and the analysis that was performed, a specification of the environment that was used for that execution, and a specification of the complete results, so that someone who was given the data, the workflow, and the environment could verify the correctness of the results that they get with that same data sources. So to these complete descriptions in each of these little domains really require sort of the complete provenance of the data, the workflow, and the execution and the results in a way that others can re-execute. Now, one can do this via supplemental information and just links and resources that are already are available to us. There are places to share data, there are places to share workflows and results, there are places to share execution environments. So the low-level implementation of this kind of thing is just writing papers with the appropriate links and citations and references, and the activities of the authors to make those critical pieces of information available at the appropriate locations. This little example here use some data from Nitric, has a DOI and is accessible there, has a workflow and results that are made available through GitHub in a particular repo, also has a DOI and a way to cite that particular workflow and results, and has a execution environment through a Docker container, which is reshareable with the world through Docker Hub. So that example was a simple analysis that anyone could do that looks at some brain volume results and makes it clear how much operating system can matter, and gives a solution to how one can solve operating system dependencies by using containerized types of environments. That wasn't really very interesting biologically, though, so another version of a re-executable publication that we've been working on seeks to answer a more interesting biological question, the broad question of what are the structural correlates of IQ in typically developing children. So we're going to try to re-explore this known the sets of observations and hypotheses with and clarify sort of the methodological dependencies that go into such an observation. So given the question of structural correlates of IQ in typically developing children, we need to discover some data and pre-register an approach. We need to expose the appropriate metadata through an IDM, which we'll talk about later. We need to select a workflow and a containerization approach that will let us answer the questions we need to ask. We need to execute that, and then we need to properly annotate the results of that and then query it and do the particular statistics driven by the a priori hypotheses. Don't want to dwell too much on this. You'll have access to the slides, but there was a set of 11 different hypotheses that we gleaned from the literature about different features of anatomy and its correlates with IQ in typically developing children. Some of these were meta-analyses, some of these were direct analyses, some of these on various brain structures, various ages, and various sexes of the groups. So this gives us a set of hypotheses that come from the literature, and our question was, can we re-execute these in a way, retest these observations in a way that expands the replicability of the ability to do that. So in this case, if one software is good, 3 softwares is even better. So when we're looking at volumes of various things, we choose in this case to use FreeSurfer, FSL, Fast and First, and ANTS as our structural software. These get containerized using NeuroDocker. These will be run, are analyzed in the cloud, AWS, Amazon Cloud Computing. The data sets come from the typicals of ABIDE and ADHD 200, where imaging and structural imaging and IQ is available, and the results are put in a open repository at SenseIn, and all the other elements of this are part of a repro repository that's accessible. Again, not to dwell too much on the ideas here, but a handful of these a priori hypotheses were confirmed. Those are the ones highlighted in green here. So in addition to the original findings, we confirm these various sets of observations. A handful of those observations were not confirmed. And we see these here. Also note that a handful of these are tested through the 3 different software tools. And in this case, the ones where we had access to relevant observations in the 3 different software tools. In this case, we're not seeing any software tool dependency in these results, but we are seeing some differences. And so again, to some extent, it's not quite so important for our discussion right now that which of these do and don't replicate. But the point is, we can take a priori hypotheses and we can now do these analyses in a way that is completely now forward, generalizable. The original studies weren't done in a re-executable way. We can't get to exactly that data easily or to that processing easily, but we're doing a similar data and a similar analysis approach, but doing that in a way that others can then generalize as needed to more data or different analytic approaches. And these are just some of the example results from that particular study. Again, not to dwell at the moment about the details of this. This is some materials that will come up in the course of the ReproRehab program. But again, this transparency comes from the provenance, from tracking the metadata and tracking the semantics of all the metadata and all the things that are going on in our study. So under the hood, again, that hopefully none of us have to deal with too personally, but be it known that each of our images have substantial amount of metadata that's tagged to it, and we need to manage and hold on to that metadata for each of the images. Each of our clinical assessments has huge metadata and information about it that's linked to the subject. The subject is linked to a session. The session is linked to a set of images. Set of images are linked to an anatomic volumetric computation, which is linked to an analysis software and a protocol for generating it. You generate results which are linked to the measures and the place where these different measures live in the relative sort of anatomic framework. So again, this is a huge linked data set of information that's necessary to get from our behavioral demographics to our imaging, to our analysis, to our actual results in ways that can traverse back and forth between these features of the data. So the original publication, in the PDF, you get a cute little picture that humanly transmits the sort of degree of correlation and sort of the degree of fit of that line. The repronym version of that, and one of these elements that that we've reproduced is very similar. A very similar correlation, very similar dispersion of the data around this significant correlation. But in the repronym version, each of these points is completely self-describing, and therefore each point knows where that subject imaging came from, knows what the MRI scan and scanner details and acquisition details and the workflow that generated it, and all of this can be traced back, so that if you have another set of data, you can generate that same type of observation. Or if you want to take that original data and process it in a different way, you can do the different approaches to looking at that in ways that are sort of regenerable and re-executable and generalizable in a much more clear fashion. Similarly, not only are the data points themselves sort of re-executable, but the statistical layer above that is re-executable. The statistical regression is provenance and metadata aware, such that it can be regenerated on different data, regenerated on the same data, and generalized in terms of its the nature of that particular statistical test. So there's a bunch of sort of best practices that pervade, therefore, how we're trying to take control of all these features that I just spent some time elaborating for you. The first sort of best practices is to really try to plan everything in advance. Things that go awry tend to be when we have to make up things later in a research plan. So trying to plan everything in as details in advance, pre-registering, and really thinking hard about how the analysis is going to go and how the hypotheses will be controlled. Version control everything so that you know what you did and when and why you change things, as we always things do evolve. So we do need to keep track of that. And version control is not, we often think of that for software, but data can be version controlled scripts, software, containers, protocols, everything that's part of the documentation of and the execution of an experiment really can go through versions and should go through versions in ways that we can track and keep track of that. Annotation for everything so that others can understand and reuse more easily what we do. And by annotation, that means when we observe something like sex or IQ or other features of our data or volumes of things, that we really make sure we express those in a semantically relevant way, so that when that data is shared, it's more self-describing and less trouble that other people or yourself in the future can understand what it was these measures resolve to. And again, annotation applies to everything, data, derived results, the processing approach, etc. Another of the best practices is to use standards for as much as we can. The use of standards makes communication with others and yourself, so much, easier down the road. And so standards for data, great. There's lots of standards in the neuroimaging community, but also sort of conceptually standards for analysis. Is sort of this idea of using containerized execution environments so that can be shared with others in a more easy fashion. Publish everything, and publish again can be broad, from sort of self-publishing or documenting, or Google Docs to preprints to peer-reviewed publications. But again, we need to document everything and put that in a place where you and your future workers and the rest of the world can access that information more easily. And again, publishing applies to everything. The data, the derived results, the processing workflows, et cetera, are all research objects that are worthy of publication and sharing, so that they can be put back together, credited, reused, and cited. So you can imagine this set of best practices that I just sort of talked about, and the desire to apply those in sort of all the phases of the research process, from the design, data collection, image processing, statistical analysis, and publishing. We want to think about how to plan, version control, annotate and describe, the use of standards, and the use of archival and publishing methods in each of these different stages. Again, I'm not going to dwell on the tools here. These specific tools that help us solve these different blocks will come up in the course of the ReproRehab program. So again, this is some more pictorial representation of again the very complex workflows that we tend to use, from data acquisition to analysis, through derived data, through the publication, and then the transformation of DICOM data into BIDS data, into a FreeSurfer BIDS app, into a container that runs that, into the volumes of a structure, into the statistical test and the publication, that the results that from, and then sort of the ReproNim re-executable version of these kinds of things is a set of tools that sort of just mildly alter sort of how we would have done that in the first place. So just the last mantra to put in here is doing truly reproducible neuroimaging research is hard. There are a lot of things we have to do to get it completely right. The first important thing is we're not going to get it completely right in our next publication. So this is a process. We need to improve bits and pieces, piecemeal, and just get a little bit better in each of our publications. And hopefully the course of this program will give you some of the tools to improve the way all of us are doing our research programs. And again, there's a lot of things that are going on, a lot of different tools, a lot of different concepts. So fortunately, we all have these programs, ReproRehab and others that are being worked on to help increase the skills of all of us in doing research and more efficiently. We're not going to go through these details, but there are a large number of resources that this course will point you to over the course of our first 3 weeks in your directed study that can help improve these different elements of things. So in summary, make sure you embrace your metadata and provenance of all of your elements of the research program and treat them with respect. The earlier you deal with all these things, the easier it is to deal with. Getting data immediately from the scanner into BIDS is much easier than putting that off. Doing the semantic representations of your data sources as you design your data capture is much easier than waiting till at the end of your grant to do those labelings, et cetera. So and everything that we know is changing and improving. So sort of continuous education sort of another important thing to keep in mind. And again, welcome to ReproRehab, and you're progressing along this educational route. Do it. Funding is becoming more and more dependent on adopting data management and best practices. Publications are getting more dependent on best practices and reproducibility. And if you don't get funding or if you don't get published, you won't get tenure, so you better do it. Late night TV, we'll make fun of, scientists who don't do proper, science from the community's point of view. So I just want to end by, the more we consider reproducibility by design, the better off and easier it is to deal with. It's not easy, but it's easier when we design for reproducibility instead of try to shoehorn our old processes into reproducibility afterwards. That concludes our sort of high-level introductions to the principles of reproducible science, our week 1 objective. I'll turn things over to JB in just a second to review some of the classical statistical issues that pervade our reproducibility topics, and just foreshadowing week 2. JB and I will be with you talking about data management and organization, and week 3, JB and I will be talking about FAIR data. FAIR is an important acronym these days: findable, accessible, interoperable, and reusable data. So those are the upcoming topics. So again, without further ado, I bring back to you, JB, for classical statistical issues in reproducibility.
Hi, everyone. This is the part of the course that deals with the issue of statistics and how to see how current statistics may not always produce reproducible results. I'm JB Pauline, and I'm from McGill University. I'd like to start with the quote from Karl Popper, a very famous epistemologist. And it basically says that insofar as a scientific statement speaks about reality, it must be falsifiable. And insofar it is not falsifiable, it does not speak about reality. So I just would like everyone to reconsider what kind of statements are being done and what kind of statistics are being done to possibly refute those statements. So let's start with the very simple notion of effect size. Effect sizes, in its very bare bone definition, is just any effect, any measurement that we are interested in. So imagine, for instance, 2 groups. There are 2 means, and the difference between the 2 means of the 2 groups are possibly an effect size that we are interested in. But often those effect sizes are standardized, and for instance, the Cohen-D standardized effect size divides that raw effect size by the standard deviation of the data, not of the means of the data. And then the Z statistics will divide by something which is more like the standard deviation of the means of the data. So this is a bare bone effect size, a very simple one, but really anything can be an effect size as long as you are interested in. But there are kind of a good and bad ones to some extent. The good quality effect sizes are simple, they are easy to interpret, they've got units, for instance, something like a height in a centimeter, or like a weight in kilogram, or things that you can interpret easily. And they're also standard in your field of research. So let's take some examples: percentage of variance, correlation, difference between means of 2 groups, and so on. Percentage of activity in the brain as measured with, for instance, board, and so on, and so on. What should be reported? What basically as much as we can and as much as it makes sense without overwhelming the reader, but making sure that we report the whole measurements and the whole the data and the means, but also the standard deviation and so on, not only the p-values. Let's take this segue to the p-value definition and what are p-values. They are clearly everywhere in the literature. So what is a p-value? So the p-value is basically when the null hypothesis is true. So you know that you assume a null hypothesis. For instance, there's zero difference between the 2 means. The p-value is the probability of observing a statistic equal or more extreme to the one seen in the data under that null hypothesis. So you measure some statistics in the data, you look at the distribution of that statistic under the null hypothesis, and you look at how much there is that value or more extreme in this null distribution. So what is a statistic? Well, basically any function of the data. An effect size is a statistic. So the mean, the standard deviation, the mean divided by standard deviation, all those things are statistics. And again, there are statistics that are more easily interpretable and communicated. Coming back to our p-value and null hypothesis testing. So we imagine a world where there are two possibilities: the null hypothesis is true or the null hypothesis is false, and we decide whether, based on the data that we have, we reject or we don't reject the null hypothesis. So the classic control type of error of control is the one that we do with the type 1 error, which is under the case where the null hypothesis is actually true. There's no difference between the means. There's no signal in the data, and we do reject that null hypothesis. So basically, believing that there is something in the signal, there is some signal in the data. And that's we try to control by saying that we shouldn't actually reject under the null too many times, and often the threshold is 5% threshold, and that's the significant threshold that is the classical one in the literature. There's obviously a very important second type of error, which is the type 2 error, which are the false negative, which is under the case where the null hypothesis is false, so there is signal in the data. Then you do not reject, and we will see that the power is basically 1 minus that type 2 error, which is basically the probability of actually detecting the signal when it exists. I want to quote Neyman and Person here, which are the two statisticians that have been developing that null hypothesis testing framework for taking decisions. And they say that we're inclined to think that as far as a particular hypothesis is concerned, no test based upon a theory of probability can by itself provide any valuable evidence of the truth or falsehood of a hypothesis. So basically, they say, don't take that framework for stating that something is true or false, which is really, really good to remind ourselves. Those are the ones that actually have developed the theoretical and solid framework for the null hypothesis testing. So what are the common problems? The most common and certainly most serious one is to consider that when the p-value is small, consider the p-value as the probability that the null hypothesis is true. So you've got a small p-value, and therefore you think that the null hypothesis is not true, or you have a big p-value, and therefore you like a bigger than 0.05, and therefore you think that the null hypothesis is true. Actually, the p-value is not about the null hypothesis or the alternative hypothesis. It's about the data and the statistic of the data. So it doesn't attribute the probability to our hypothesis. So I'll take this second example with defining why there's often misinterpretation of the p-value. If a study is conducted with a control type 1 error, say 5%, an adequate power, let's say 80%, then significant results almost always are corresponding to true results. And I want to point you to this Blow et al. Paper in 2010 that describes very well how that problem occurs, and which shows the problem. And the almost always here in that scenario of a 1,000 null hypothesis and a 5% type 1 error and 80% power, the almost always here will be 64%. So 2/3 of the actual detection are actually true, which is not a great number. I mean, it's better than nothing, but it's actually not. It leaves a lot of space for having detection and not an actual signal. Power. let's go back a little bit to that notion, which is really critical. As I said, it's 1 minus the type 2 error. And if you look at that curve here, that graph here, the null hypothesis is in blue. The threshold at which you're going to say that you reject the null hypothesis is in the red vertical bar here. And the alternative hypothesis here is in green. And therefore, the power is just the curve, the integration of the curve, a bit on the right of the vertical red bar here of the alternative hypothesis distribution. The distribution of the statistic under the null under the alternative. So power is a key measure, because without good power, the study is really not worth doing. You don't have a chance of actually detecting something, even if there is something. But also because when there's not good power, the study results are doubtful. Power is hard or very hard to measure. You have to know the null, you have to know the alternative, you have to know, therefore, effect size, variance, all those things, and to choose, of course, the threshold. And despite that it is very hard to estimate, it is absolutely critical that we try to estimate it and get some sense of how much power, how much data do we need to get a reasonable power for our particular study. I'll take this classic example of Mulajic that looked at the association between the BDNF variant and the size of the hippocampus, and looking at, on the x-axis, the time of the publication, on the y-axis, the effect size found in those publications, with the sample size being represented by the circle here on this graph. And you see that the small circle, early publications, so effect sizes are quite high, a little bit all over the place. And then as soon as you increase the sample size, the study sample size, you get small effect sizes from even close to zero, possibly equal to zero. So small samples lead to very variable effect sizes, and only when you have large samples you can actually assess properly the effect size, and therefore, and in that case, show that there is actually no effect size, or very or likely zero effect size. What is p-hacking? Well, p-hacking is the classic problem that, first of all, is probably not intentional most of the time. That you have a study, you're trying to do some statistic, and you really want to find something in the data because the data have been long and difficult to acquire and costly, and therefore you're going to analyze the data in a number of ways, such that at the end there is something that will be at the statistical threshold of less than 0.05. That is p-hacking, because you, by exploring many ways of analyzing the data, you are increasing the type 1 error. And in this classic Simonson 2011 paper, they show that procedure can go can lead to extremely large type 1 error, 60%, sometimes more than 50%. So there are tests to actually know whether in the literature there is some p-hacking, which is interesting. So again, that's not about, this is not about fraud. This is just about bad standards and bad practices in terms of data analysis. And there is a solution to that, which is slowly implemented in the literature, too slowly, but still there is some movement in that direction, which is pre-registration, where you actually specify exactly what kind of analysis you're going to do, and then you can ask the journal to review your plan, and if the plan is accepted, then the results will be published, even if those results are not significant. So that's a very interesting procedure. There are other possibilities. You could also increase the type 1 error. You could complement with other statistics and so on. But I think p-hacking can be very well solved with pre-registration. It just has to be implemented. What is the Faldor effect? Well, in some sense, it's actually linked to pre-registration as well. Faldor effect is simply the fact that when you're looking at the literature, you are unlikely to see non-significant results. And therefore there's a lot of studies that are being in the drawers and that are not being published, and therefore the effect size that we find in the literature are kind of biased towards higher values. So if you look actually, so the Fandor effect is really, sort of promoted by the academic incentive to publish and by the constraint that the journal will ask you to have significant results, statistical significant results, and therefore it can lead to p-hacking. But if you don't p-hack, you may have a lot of a Fandor effect, which is because the journal won't accept the non-significant results. So most of them or most of the time. So this thing can be actually quite well seen in the literature, where if you look at all the z values reported in the literature, you see like a big gap or hole in the between -2 and 2 because of that non-reported z values for non-significant results. The remedies, again, I think pre-registration is a very good answer to it. Also advocacy to journals and also I would say it is important, very important in the case of null results, to be able to establish what is the power or have a good idea of the power of the study, because a null result with a low power is really not interesting. It doesn't bring information to the field. But a null result with a lot of power brings a lot of information to the field, where you assess that indeed there is actually no interesting signal in the study. I also can think of different kind of statistical framework, or like a predictive framework, or Bayesian analysis, and so on. I also would like to define what is the winner's curse. So the winner's curse is in the situation where you have predetermined threshold, where you will say that there is a statistical significance, when p is less than 0.05 or 0.001 or and so on. Then and especially when the study has a small sample size, and the statistical threshold is stringent, then you have an overestimation of the effect size. So by definition, you're going to report only effect sizes that are above a certain threshold, and that leads to an overestimation. So the impact on the literature, where the effect sizes are reported, are going to be sometimes vastly overestimated. There's a very interesting paper by Marek et al. About the low samples effect size that can be found in the literature when you're looking at a very, very large sample size in the UK Biobank, for instance. Almost the last one, not entirely the last one, the positive predictive value, the PPV, or positive predictive value. So positive predictive value is an interesting probability. It's the probability that the alternative hypothesis is true, knowing that the test is significant. So let's say you have a significant test. You've taken the data, you've done statistics, you've done an hypothesis testing procedure. The test is significant at a given type 1 error. And then what is the probability that your actual alternative hypothesis is true, knowing that that test is significant? So it's a kind of a different framework, because the alternative hypothesis is now something that you can attribute a probability to, but it's a very interesting probability to get, because that's the one we are interested, right? The probability that the actual alternative hypothesis is true. So it's worth concluding. Is it worth concluding anything if that number is small? Probably not. That we're not interested in the probability of the value of the test itself. We're really probably interested in the hypothesis that we have. So that probability PPV depends on the prior probability of how likely the alternative or how likely the null are, and their ratio of and also on power, as well as on alpha, the type 1 error risk. So you can easily compute that number when you have those three things. So W power, R the odd ratio, and alpha the type 1 error. And look at that graph, for instance, if you increase or decrease power. And if you have a small power, let's say 0.3, for instance, or 0.4, which is not unheard of, the PPV is about 0.5, 0.6 maybe. So you only have maybe half of the time the probability, the alternative hypothesis will be actually true. That's with alpha equal 0.05, but let's say there is some p-hacking and you are actually not controlling very well the risk of error. Maybe 0.3 is the actual risk of error, and then suddenly the PPV, even for like a good power, is going to be very, very small. So the combination of p-hacking and some and computing that number is interesting because it will tell you the sort of the detrimental effect of having an uncontrolled type 1 error. This led this all studies. They started with with Ioannidis et al. Was led to this interesting paper, which look at the effect size with a small PPV and small power, and look at the PPV under the number of conditions. But also look at the number of neuroscience papers that have low power, and therefore that's those kind of problems in their studies. Last, a very quick note on statistical generalizability. It is often the case that the notion of what is random and what is fixed in a study, in a statistical model, is not very clear, or it's difficult to grasp. And if a model has actually fixed effect that should be random and should be considered as random, and therefore taken from a distribution, and those effects will have much larger variances, and therefore the significance will be less, and but will be a better representation of the actual of the reality. So be careful with the actual modeling of fixed and random effects in the literature. I think that's it. So it is critical to understand the statistical framework that we are usually working with and its limitation. And I hope now you have some ideas of what is the Faldro effect, the winner curse, the p-hacking problem, and possibly a problem of statistical modeling. Thank you for your attention, and I hope this was useful.